The traditional DC motor has a high rate of wear and tear due to its carbon brushes. That is why this motor is replaced more and more by the BLDC motor. Since the commutation is done electronically, the BLDC motor can perform high rotational speed with high efficiency. Let us dismantle this drone and have a closer look. The rotor, the moving part of the motor, consists of permanent magnet. What you see here is the outrunner type. The rotor will rotate synchronous to the rotating magnetic field of the stator because of its permanent magnets. To explain back EMF in a few words, when the rotor passes a stator coil, a voltage is generated within this coil. The back EMF is proportional to the motor's rotational speed. It's up to the electronics to evaluate these signals. Centerless BLDC motors have only 3 wires. Brushless DC motors offer significant advantages over standard brushed motors, especially at high rotational speed. With its high efficiency, high reliability, and less wear, this motor is used for examples for ventilators, tools, model kits. The BLDC motor can be characterized as a synchronous DC motor.
Electric motors are the backbone of modern automation. Motors convert electrical energy into mechanical energy, and the resulting motion and torque drives a load. A simple DC motor has a stationary set of magnets in the stator and an armature with insulated wire wrapped around a soft iron core that concentrates the magnetic field. The windings usually have multiple turns around the core, and in large motors there can be several parallel current paths. The ends of the wire winding are connected to a commutator. The commutator allows each armature coil to be energized in turn and connects the rotating coils with the external power supply through brushes. The total amount of current sent to the coil dictate the strength of the electromagnetic field created. The sequence of turning a coil on or off dictates what direction the effective electromagnetic fields are pointed. By turning on and off the coils in sequence, a rotating magnetic field can be created. These rotating magnetic fields interact with the magnetic fields of the magnets, permanent or electromagnets, in the stationary part of the motor, the stator, to create a torque on the armature which causes it to rotate. The brushed DC electric motor generates torque directly from DC power supplied to the motor by using internal commutation, stationary magnets, and rotating electromagnets. Brushes are usually made of graphite or carbon, sometimes with added dispersed copper to improve conductivity. A brush holder has a spring to maintain pressure on the brush as it shortens. Advantages of a brushed DC motor include low initial cost, high reliability, and simple control of motor speed. Disadvantages are high maintenance and low lifespan for high-intensity uses. Typical brushless DC motors use 1 or more permanent magnets in the rotor and electromagnets on the motor housing for the stator. A motor controller converts DC to AC. This design is mechanically simpler than that of brushed motors because it eliminates the complication of transferring power from outside the motor to the spinning rotor. The motor controller can sense the rotor's position via Hall effect sensors or similar devices that can precisely control the timing, phase, and other aspects of the current in the rotor coils to optimize torque, conserve power, regulate speed, and even apply some braking. Advantages of brushless motors include long lifespan, little or no maintenance, and high efficiency. Disadvantages include high initial cost and more complicated motor speed controllers.